So hello everyone, I'm Andréane from the team of ENS de Lyon representing France, and today I'm going to present you the subject of the half-empty bottle. So first, what is the subject? The subject is if you push a horizontally lying bottle half full of water, it will roll forward with an oscillating speed. So you can do it with your bottle. And the question was, what does the magnitude of the oscillation speed depend and how? So first, the main parameters in this study. So the main parameters is first the viscosity of the fluid. It's also the masses, both of the fluid and the bottle. You can also consider the ratio of filling, the diameter of the bottle, and the time for the damping of the oscillations. So, because of the shape of the bottle, we have decided to use a cylindrical tube for all our study. So, let's speak about the hypothesis of the problem. First, in the subject, it is said that it is a half-empty bottle, so the ratio is fixed. Also, the fluid is water. And for our study, we consider that the surface of water is plane when there is oscillations. So the main parameters here are the masses of the fluid and the bottle and the diameter of the bottle. So this is the outline of the presentation, so I will try to give you a simple explanation of the physics of the problem. So first I will begin with the coupling between the fluid and the bottle. Then I will speak about the hydrodynamics and the sloshing, and I will finish about the magnitude of the oscillations in speed. But first, to understand the coupling between the fluid and the bottle, I want to do a very simple experiment right here. And so you have two cylinders, a hollow tube and a full cylindrical tube. And I want to ask the whole audience and the jury which one is going to be the fastest one. So please raise your hand if you think it will be the hollow tube. So Clément is going to show you the experiment. And what you can see is that the full cylindrical solid is the fastest one. And this is not because of the mass, because the mass doesn't matter here. What matters is the mass distribution. And so the inertia momentum of the hollow tube is higher, and so it is going to be slower on this kind of inclined plane. Now I want to ask a second question. With a full cylindrical tube and a cylindrical tube filled up with green water. Who thinks the tube filled up with water will be the fastest one? Please raise your hand. So let's show the experiment. And so what you can see is that the tube filled up with water was the fastest one. And this is because the moment of inertia of the tube filled up with water was lower, and so it contributes less on the inertia momentum according to its mass. So this is the experimental results because we studied it in our university. And what we found is that in yellow here, you have the empty bottle, so the hollow tube, which is the slowest one. In blue, you have the full cylindrical solid. And in red and green here, you can see the half-empty bottle and the full bottle, which confirms what you have just seen. So how can we explain this? So we can explain it very simply. Here is the half-empty bottle filled up with water, and there is a boundary layer right here. And what is the main important fact here is that there is a decoupling of the rotation of the fluid inside the water and the rotation of the bottle. And so I want to ask you another question. If I turn a bottle, if Clément spin up a bottle at a constant speed, how long will it take for the water inside the bottle to spin up with the bottle? And so the answer of this question is simply given by the Navier-Stokes equation. If you consider the Navier-Stokes equation, you can define a diffusion time, which is linked to the viscosity and the radius of the bottle. And this diffusion time is way higher than the duration of our experiment. So this simply confirms that there is a decoupling of the rotation of the fluid and the rotation of the bottle. And so now we know it's decoupling. I want to present you this setup right here. So what is it? Here you have two wheels that can rotate and independently from a half cylinder solid. And so this is interesting because we can study the movement of this model. And this is what we have done. we have considered the kinetic energy. So both the kinetic energy of the wheels and the kinetic energy of the half cylinder. And we can also consider the potential energy, which is due to gravity. And if we use the Euler-Lagrange equations, we can obtain two differential equations, in which you can recognize here the term which is the same as for an harmonic oscillator, with here the angular frequency. And you can also notice that in the angular frequency, here you have the term that is the same for a single pendulum, and here you have the coupling term. And also, in this second equation, you can remark that it's simply the equation given by the angular momentum conservation. And so here, the angle is the angle of the water inside the bottle, and x is the position of the whole system. So we make an experimental validation for this simple model. And so we measure experimentally the period of the oscillation by making a spatio-temporal analysis, and it's in excellent agreement with the theory we have just seen. But the movement of the water inside the bottle is not the same as for a solid because of the sloshing. In fact, what we can see in here, which is a picture of our experiment, is that with the little tracers right here in the water, the nearest the particles are near the surface, the greater the speed will be. And far away from the surface, it's really slow. And so this was studied by Lord Rayleigh over a century ago. And what Lord Rayleigh do is that he defined an inertial momentum for sloshing. And this was also studied by them in 1945, which gives an analytical solution for the feed velocity. And here is, by using this analytical solution, we can obtain the same experiment theoretically for the speed of the fluid in the bottle, which confirms that here the speed is higher than far away from the surface, such as you have seen on our experiment. So let's talk about the sloshing oscillations. So we can use again the same differential equations as before, but in the angular frequency, now we have to consider the correct moment of inertia, which is defined by the sloshing. And so this theory confirms what we experimentally obtained for our bottle. So the model of sloshing is really appropriate to describe the half-empty bottle. But the question of the problem was not about the angular frequency, of the oscillations, but about the magnitude of the oscillations. How does it depend and on which parameters? So first, I want to insist really on the importance of the initial conditions to obtain the oscillations inside the bottle. So first, if you push just gently the bottle, just like this, you won't have any oscillations. But if you kick it a little bit more, then you will see oscillations. And so it's really hard to define the transition between no oscillations and oscillations. So to do this, we used this kind of setup. So here you have the bottle, and here you have a wall. And first we are going to consider the approach of the bottle with no oscillations inside the bottle, then a bounce on the wall, and then it will get off the wall with oscillations. And we made this setup to control the initial conditions so that we know all the initial conditions just right here. So this is the video. And so here you can see the oscillations. So this is the experimental setup. First, there is the approach of the bottle with no oscillations inside it. Then there is an impact on the wall. And then there is a rise of the fluid on the side. It hurts the wall. Then the water is going to come down to a horizontal surface. And when it's beginning to rise on the other side, then the bottle gets off the wall. And what we can see then is that there are oscillations inside the fluid. So we can study this theoretically by considering that there are no energy losses in the impact and also no friction. And the conservation of the energy gives us this kind of formula. In this formula, you can consider here the term which explains the oscillations with the angular frequency I've just defined before. And also, what you can see is that here we have the amplitude of the oscillations in speed, which involves the different parameters, the different masses, and the moment of inertia of sloshing. So now I want to validate experimentally this theory. And so here in orange, you have our experimental data when we tracked the position with the software. And so here you can see the approach of the bottle with a constant speed, then the impact on the wall, then there is half a period when the bottle is on the wall for the rise of the fluid, and then it gets off the wall and it oscillates. And in green, you can see our theoretical curve. So it's not a fit of our data, it's a theoretical curve when we use this formula. And what you can see is that there is a perfect concordance between the theory and the experiment. So as a conclusion, the question was, what does the magnitude of the oscillation in speed depend and how? And so first, there is a high dependence on the initial acceleration and the initial conditions. To avoid that, we made a bounce on a wall. Moreover, there is a dependence on masses, both of the fluid and the bottle. There is also a dependence on the geometrical parameters, so the radius of the bottle, the thickness and the length of the bottle. There is also a dependence on the ratio of filling, because, for example, if you take a completely full or empty bottle, there will be no oscillations. And there is also a dependence on the viscosity for the dumping over a long time. So as a conclusion, I hope you enjoyed this presentation, and I will just say that maybe it's a little too pessimistic because the bottle was always half empty.
Thank you. Opponents, you have 2 minutes for technical questions.
Thank you. Which parameter dependencies have you studied?
Well, the masses, the radius of the bottle.
And have you in experiment?
Well, yes.
Okay, thank you. Did you verify experimentally if the surface is really planar?
The surface of what?
Of the
yes.
water, if it's a plane.
Yes.
What was the value of the Reynolds number in your system?
The radius number, well, it was something low.
Okay, so do you think the viscosity has a significant influence on the shape of the flow?
On the shape of the flow?
Yes.
No.
Okay, have you experimentally, could you just show us slide 20, I believe? The one with comparison theory experiment. With
20 is this one.
With the sign, green sign, orange points.
Yes.
Thank you. Are there any fitted parameters in this theoretical curve?
No, absolutely not once.
So how did you determine the value of velocity 0?
Here? No, I don't understand.
So could you
This
show us
the
your
initial here?
So one slide earlier then. Maybe I can explain easier. There
This
is
bit?
velocity 0. How did you determine this
Oh,
parameter?
this one we didn't determine it. It's why there is no theoretical curve right here.
Okay,
We
we'll
can
come back into
determine
the
theoretically the speed of the bottle, which begin right here when the bottle is on the wall.
Thank you. What are the assumptions for deriving the Rayleigh formula for effective inertia?
Sorry?
What are the assumptions for deriving the Rayleigh formula for effective inertia? You are using certain formula to model the pendulum of the water.
Yes.
What are the assumptions of this model?
Thank you very much. Opponents, you have 2 minutes to prepare.
Welcome, ladies and gentlemen. My name is Rados Waszkiewicz, and I'm going to show you Polish opposition to problem number 12, half-empty bottle. So there are several parts of the problem content that are needed to explain fully for an optimal solution of this problem. So first of all, it is said that if you push the bottle, so I believe that determining the dependence of the amplitude of the vibrations on the initial conditions of the bottle movement are really important, and it was done in some way because it is possible within your experimental setup to vary the initial conditions, but you haven't shown that you really did vary them, and if your model really predicted what would happen. It is said that we should investigate the magnitude of the oscillations. So you proposed a method of measuring the velocity oscillations. I don't know how did you come from the position to the velocity, but I believe it would just be a simple difference. So it was done quite well. You have a method that allows you to study this problem, so you should use it to verify your theoretical model. And in case of the dependencies, we haven't seen any experimental validation of your theoretical model if it really is applicable in the system. You simplified the movement of the fluid inside the bottle just to the solid half of the cylinder. So I think that verifying if this simplistic model is really applicable and how the parameters of the fluid, of the bottle, and of initial conditions really influence the phenomenon. So to your theoretical model, you provided a qualitative description of what happens and why is it different than just a simple bottle filled or empty, and why the oscillations of the fluid change anything in this phenomenon. And your theoretical model was based on sloshing, which is a good point, but I don't understand the leap between the sloshing and the solid state approximation of the half cylinder. So in case your theoretical model, you said that there is a viscosity, and then you say you use Euler-Lagrange equations, which are conservative equations. So there is some ambiguity in your theoretical assumptions, and initial conditions were not investigated theoretically. I think if you are sure of your model, you could at least sketch the dependencies theoretically to let us know if your model has a predictive power. So in case of experiment, you live presented everything, so that's great. Everybody loves it, and we could really see if it works or not. But you had one comparison between theory and experiment, so it's a pro, but at the same time it's a con, because it's only one experimental comparison. I know that we can fit to some points a sinusoid, but I wouldn't call it an investigation of the applicability of the model. So there was no verification of the flow velocity profile, as you had theory for this, and only base mode was investigated, and higher modes can also be excited in the bottle. And it's a quite interesting phenomenon where you can really see that the fluid sloshing is what causes the interesting phenomena in case of this problem, not just the simple movement, like pendulum-like movement. The initial conditions, you had a way to vary them. You didn't present the results. What happened if you really did vary them? And I think to investigate it thoroughly, you need a separate control of the bottle and fluid velocity. In your case, these two were coupled, and initial velocity of the bottle was set in the same moment as the initial velocity of the fluid. So it's just one of the possible configurations. We can imagine a setup that really, as in it is said in the problem content, pushes the bottle. So the bottle has velocity, and the fluid has little to no velocity. And this is a qualitatively different phenomenon. And I would like for you to comment if your model is still applicable there. And I think that in case of the presentation of the comparison, there are fitted parameters, for instance, the V0, which is taken from the experiment. So you should clearly distinguish which parameters are fitted and which are calculated from the theory. So let's now go into the discussion. So first of all, could you show us your experimental dependence on the initial conditions?
Well, yes, of course. So first of the model for Pershing. So yes, it's what I wanted to explain right here, is that there is a huge dependence on the initial conditions, such as you notice. And here, the validation of this formula is for a given initial condition, which is ours in our experimental protocol, and it works. If you push,
so have you verified if this formula works experimentally?
Yes, of course. It's what we have done here.
It's just one measurement, or there are multiple measurements to verify it?
Oh, there are multiple measurements. It's a choice to show you only one, because we think it was more easy to understand the physics with one curve than many curves on one graph.
I believe showing the dependencies on the parameters that you claim are important in this phenomenon is an essential part of the investigation. For instance, you could plot the amplitude of the velocity change on one axis, and on the other axis, the V0 parameter.
Right.
So in case of this measurement, how do you determine the V0 parameter?
Here, theoretically?
I
Or
mean, how did you
experimentally?
obtain this graph?
Which one? The orange or the green one?
So the orange is from the experiment.
Yes.
So
The green
I
one?
think I understand how, but the green one.
Well, the green one is determined at the time the bottle is on the wall. So the speed of the bottle right here is of 0. And there is half a period when the fluid is going to rise on the side of the wall and to be horizontal. So this is why there is here a speed of 0 for half a period
So
time.
V0 is calculated from this distance t divided by 2. The parameter V0 is one
Yes.
of the parameters of your theoretical model, or at least an initial condition. So how did you determine the value of it?
Well, it's determined experimentally by the arrival speed
Okay,
of the...
so I think you can agree that there is a fitted parameter, as you said that there are no fitted parameters.
Well, yes, okay. Well, only the initial
Great.
speed of the bottle. Sorry.
Great. So now we know. And in case of the frequency of oscillations, they were determined theoretically or experimentally?
Which one?
The frequency of oscillations.
Well, both, to verify the theory.
So in case of this green line,
The green line is theory, only theory.
okay,
So
so
the
the only
pulsation
fitted
here-
parameter is V0.
Yes.
Okay, so have you checked any dependence of the frequency on the parameters that are important in the model?
On the frequency, yes. Well, yes. With this formula.
So you have a theoretical model that you claim that has a really big predictive power, and there are multiple parameters here. For
Yes.
instance, the radius of the bottle.
Well-
Have you verified that this model works for multiple values of Al?
Of the radius of the bottle?
Yes.
Well, yes, it changed the frequency because dependence of the period is linked to the square
Yes,
of the radius.
I understand the relation, but I'm asking if you verified it experimentally.
Yes, we verified it, but we not only change the radius, because when you change the radius of the bottle, you will also change the masses of the fluid inside.
Okay,
So
do you have
change-
these measurements with you to show us?
No, no. So I did not-
That's quite a shame. Okay, so at the very beginning of your presentation, you said that viscosity is a very important parameter.
Of course, and
So, yeah, let's come back to one of your slides when you tell us something about viscosity.
right here.
Okay, for instance, so what you're saying is that the boundary layer forms and the fluid oscillations are coupled with the bottle.
Yes,
So how would you estimate
No.
the value of the Reynolds number in this system?
the Reynolds number.
Yes.
Well, you can define two Reynolds number, I think. And when I say it was a low Reynolds number, it's in the boundary layer, because here you can't neglect the viscosity, and it's here that the viscosity is preponderant. But in the water inside the bottle, which is decoupled from the rotation of the bottle, here you have a huge Reynolds number.
30 seconds.
So is viscosity important or not
Yes,
for
it's
modeling?
Well, it's not
So how
important.
So how do you take it into account in your theoretical model at the end? Could
Well-
you show us the equation for
Yes,
this
of course.
green line? Okay, so,
So
is
here-
there a viscosity
No,
here?
no, and I will explain you why. Because here we have only 4 seconds, so it's a very small time. But if we consider the damping of the oscillations, such as we can do right here, with a huge time, then you will consider the viscosity, because all the energy is used in the
you.
viscosity of the solution.
Thank you.
So now it's time for technical questions from the reviewer, please. 2 minutes. Time out.
Good afternoon, ladies and gentlemen. My name is Alexandra Maslakova. I represent the team of the Russian Federation, and I'm going to present you our reviewing of the problem number 12, half-empty bottle. Now let's begin with a brief reviewing of the reporter's work. She showed us a lot of live experiments of rolling some cylinders, like half or empty, or half empty, sorry. Well, then we saw some theoretical estimations about the oscillations of the speed, which was required by this by the problem task, and then then she showed us only one experiment, and it was compared with the theory. But the theory was actually we noted from the discussion, semi-empirical. So one of the parameters was fitted, so I think it can be considered as the real theory. Okay, the advantages of the reporter is live experiments. She considered the momentum of inertia of liquid like not in a solid body, but then she took the water as a solid body for her mathematic. Then she made a model of solid pendulum, which is kind of not connected with the second point. Controlling of initial conditions was quite good, but still there was lack of experiments. Okay, points to improve is the rolling from a slope is not a push, but okay. Then after the discussion, she said that the Reynolds numbers are low, but no, they are big. And there are no investigation on dependencies of parameters, which opponent actually said. And his comments were relevant and reasonable. I liked his opposition. And the disadvantages of him is that he disagreed with the model of solid object, but it can be quite good for mathematical estimations because it's more simple than water. Then he paid too much attention during the discussion to dependencies on parameters. And actually, he didn't improve the solution, just because the whole discussion was about the parameters. Like, did you change the parameters? No. Did you change the parameters? Again, no. So I'm going to show you my questions for the discussion. And the first and the most important is, what are the conditions when water cannot be considered as a solid object? So I suggest the opponent and the reporter to discuss this point. Thank you. 4 minutes. Yes.
Okay, so I believe in this problem. It's not the very best way to approach it, to consider the water as a solid body, because
and as a fact, we didn't
the higher modes.
We didn't consider it was a solid because can I switch?
Oh, sure.
Because when we calculate the angular frequency of the oscillations of the water, we involve the moment of inertia of sloshing. So this is taking into account the movement proper to a fluid. But we can consider that we can study the movement, which is the decoupling movement of two oscillating bodies, and so this is mechanical solid.
So what are the assumptions for developing this ice slosh?
The assumptions for using
Yes, you use the Rayleigh equation, I believe.
Here, right here.
Yes. What are the assumptions for developing this formula?
It's only that you have a liquid into a cylindrical object.
I have a question for both of you. Actually, in qualitative, simple physics, what is the physical origin of the initial angle? Why does the water splosh, as you said?
When the water splosh,
I believe it's stopping of the bottle. Could you just allow us to finish on this formula?
Well, not stop. Well, I asked the question, so please answer my question. What is the physical origin of the initial angle? Not stopping. Yes, I got your point. But still, if the water, if the bottle will stand, and then we push it, there will be some initial angle of the water. And what is the physical origin of it?
It's the acceleration of the body.
Acceleration. Thank you. I like your answer.
Okay. So I believe in fluid dynamics, it is important to consider the assumptions behind such models. And in this model, there is no viscosity, for instance. Do you think that it was developed in a potential flow approximation?
Well, it's valid if the radius of the bottle is large in front of the boundary layer where the viscosity is important. And this is the case for our study, because the radius of the bottle is of 5 centimeters and the boundary layer is less than 1 millimeter.
How did you estimate these values?
Of the boundary layer? Yes. With the Navier-Stokes equation. Well, did I? Here, right here. So here you have an equation, and here you can consider the evolution of the boundary layer, which evolves in the time. And so for the time of our experiment, we can apply this formula for 10 seconds, for example, if our experiment is of 10 seconds long. And we can calculate the value of the
so it's
boundary layer.
Characteristic length of the boundary layer.
Yes.
So do you think that validating the size of the boundary layer is enough, or are there any other things that you need to consider to apply potential throw approximation?
To consider what?
So maybe one remark just before this. Do you agree with me that the Rayleigh formula is developed in potential throw approximation?
Well, it's developed in modes of sloshing, yes.
So is it potential throw approximation or not?
Potential?
Potential throw approximation. It's a simplified theory, not full terms in the Navier-Stokes equation.
Yes, of course.
So
And
to exclude some of the nonlinearity.
yes, and I told you again, in the water inside the bottle, you can consider you have no viscosity. And you can, well, very simply verify it. Take a
Okay, so
rotating
do you
water.
think
Excuse
that
me. Can we move to another question?
From now on, the teams
Okay,
can
yes,
intervene
I
in
know, and since there are no questions from the teams, I'd like to discuss the methodic of experiment, because you said a lot of disadvantages of experiments. So how can you suggest to improve?
make more than
this-
one experiment and show it?
Yeah,
The
I
one-
agree.
more than
More
one.
than one experiment, and then we will get more graphs, and what about experimental setup?
Yes.
I think we can not the roll bottle and then it will stop by the wood thing, but we can push it. It will be standing, and then
Yes.
we will push it.
Yes.
I think the main reason
That
to
would be
do
better.
experiments is to verify the theoretical model. So
Yes, but we have done this. So let's move about the question. So yes, we can do another setup, but it was really hard to control the forces and the initial conditions to apply on the bottle. But there are many ways to do it. I don't know. Well, this is the best
I
setup
don't
we have
agree with
chosen.
you.
I
don't
think
agree
this
with you.
setup is sufficient for studying this phenomenon. You could use multiple bottles, multiple fluids, multiple initial velocities. There is so many parameters that you could have varied, but you did
But
only one experiment.
Dear
At least
No,
in
I
your
Wait,
showed
we
you.
formula.
got
I showed
your
you only
Sorry,
one experiment.
Why?
excuse me. We got your point during your opposition. She didn't make a lot of experiments, and we have questions from Polish and Russian team. So well, let's start with Polish.
How the mass ratio of water and the bottle influence the amplitude of vibrations, of the velocity variations?
Sorry, the ratio of filling?
The ratio of masses.
The ratio
Because
of
you
masses.
said the ratio of masses is important, I would like to ask you how it influences the amplitude of
Yes, of course.
vibrations.
I understand. So you can see right here that here you have the two volumic masses, both of the bottle and the fluid, with two geometrical parameters, so the two head right here and here. And this is the dependence of the amplitude of the oscillations with the
Does
volumic
this
masses.
function have a maximum?
Well, yes, I think so.
For what ratio?
We didn't study it because the volumic masses of the fluid was imposed,
Okay.
and we used only the plastic
Okay,
tube
s-
to
So why
validate the
is
model of the
the
bottle.
dimension of this formula, it has no unit? It
Well,
should be
yes, it's only
amplitude.
it's the adimensional forms of the amplitude of the oscillation, just to show the dependence on the volumic masses.
Excuse me, what do you want from the reporter?
I would like a theoretical dependence plotted on a graph and compared with experimental data, also discussing the important properties such as the maxima,
Okay.
minima, and the asymptotic behavior.
We know there is no experiment, but okay, I agree with you. Next question, Russia.
I have two small questions. At first, please come back to your formula. I have a short question about it.
This one?
To formula with the square root with dependence from... yes, here. Please, could you answer if we took the bottle with really big density, could we have a negative number under the square root? I think it's very,
No.
very strange.
No, because here the little l is the value of the thickness of the bottle, and here it's the length of the bottle. And so in our experiments, we take a very little thickness in front of the shape, the length of the bottle. So
The
no,
question
it's not
is
possible.
about theory, not the experiment. We know that
Yes.
you use the plastic bottle, but if we will take a very massive bottle, what
Well,
will change?
Well,
Yes.
the
There
bottle.
will be some, yes.
Well, then the bottle won't move, but you can have only oscillations inside with the
I
water.
believe
Yes.
the question
Yes.
is
I
about
agree with it.
validity of this formula.
Sorry?
Because we would have the square root of the negative number if the raw
No.
bottle is very big.
1 minute.
Well, yes, if you take a huge thickness for the bottle and a very small length, so it's just a cubic plastic cube, I think.
Dear opponent, can you agree with us that there will be no oscillations?
In which case?
If there is a negative on the square.
I believe there is some problem with the formula here.
No, there is not.
Okay, but still there will be no oscillations. I agree
If
with
we
the
have
reporter.
no fluid and just a solid bottle, we observed it even in the real life presentation that there are no oscillations. So yes,
Yes.
obviously there are no oscillations.
Okay, thank you. Is there any questions? Again, Russia?
Short question. Could you physically explain why the momentum of inertia of fluid is different from the momentum of inertia of solid body?
Well, yes, of course. It's because the fluid has properties that a solid don't have. And if you take a half cylinder of solid, the farthest you will be from the surface and the more you will go quickly around the center.
Yes,
Thank
you.
it's
Thank
okay.
you.
It's okay.
So, reporter, please conclude in 1 minute.
So first, I want to thank both the Polish team and the Russian team, which I think really make a good review of this work and really animate the debate. And I want to insist that even if I showed only one experiment, it was to make things maybe a little clearer and to insist on the physical aspect of the presentation. Well, I also want to thank both my team and the other team in this tournament because I think we all have a very good week and also the organizers for this week. Thank you.
So now it's time for the questions of the jury. Jean-François Joanny.
Can you explain exactly what sloshing is and what the Rayleigh formula describes?
Well, yes, of course. It describes that a fluid doesn't oscillate the same way as a solid because I think we all know that a solid, when you are far away from the center of the axis, the quicker the point will go. And it's the difference with a fluid because you can make the experiment with tracers in it to show that here it's the contrary to a solid and the sloshing is the point that the nearest you are from the surface of the fluid and the speeder you will, the more the speed will be high.
Yves Bréchet.
I have a question concerning viscosity. Is it clear that it's going to only to damp the oscillation in the long term, or are you going to have some extra phenomena? I mean, if you took a mixture of water and glycerin, they are both miscible, and you can have 2 orders of magnitude in difference in viscosity. So have you tried to look at a different viscous liquid, and are you sure you are not going to have some extra effects rather than damping? I mean, including dissipation inside the liquid.
Well, I think if they are miscible, then you can define one term for the viscosity.
Yes.
And I think it will oscillate the same way. It will only change maybe the boundary layer for the dissipation.
What I meant is that you have one term for the viscosity, but
Yes.
you have for the same liquid, you can have viscosity which is changing by 2 orders of magnitude, which is a nice experiment to be done.
Yes, but then you will change the damping of the oscillations.
Only.
Well, yes, in our study, well, it will change the part where the fluid is oscillating because you will have a huge part of the boundary layer and so a smaller part for the oscillations of the fluid inside the bottle.
Yeah. Okay.
Okay.
Try to do the experiment.
Oui. Si vous pouvez m'aider, merci. Thomas Flynn.
Can you go to the slide you have of your theory versus experiment, please? The green and orange one. Now, I'm curious about this because it looks like we've almost got a periodic step function in the middle. Your theory tends to match very closely on the left 3 and the right 3, but in the middle we seem to have a raising of your experimental data. This is within the error bars, but because your data matches so closely, I was wondering, do you think there's any underlying physics that could perhaps cause an oscillating step function, or is this simply an anomaly in your data?
Well, I think here we consider this only the term that there is the energy conservation, and I think we neglect all the energy losses, which can maybe explain the differences. but I think this is an agreement with the theory, so we didn't have to consider it.
There was some additional plot shown with viscosity how the oscillation is damped.
Yes.
And this damping is on the order of 1,000 seconds.
Yes.
And I wonder, is the bottle really rolling for
No.
1,000 seconds?
No, the bottle is not rolling, but the water inside is still oscillating.
Thank you.
Okay. There will be a small question to the opponent and reviewer, because they good word just saying. What do you think would be the best improvement of the work made by the reporter team?
Verifying the theoretical model.
Okay, next one.
I agree, and the second point is that actually on the plot with this theory and experiment, this amplitude should be less and less and less, and then comes to zero.
Yes.
Okay, so
Okay, if you have time, then I will
Yeah.
ask another question to all three of you. For the model with, instead of water, with this solid thing, could you close the presentation and try to write the Lagrangian on the blackboard? The Lagrangian was shown, but I just wonder if you can reproduce the Lagrangian that you show in your presentation, and if you can write this Lagrangian. And please close the presentation, just not to see the Lagrangian. Okay. Yeah, that's it.
I did.
Где он находится?
Дай время, слушай, так быстро написать. Мне кажется, здесь можно.
Last question: is the oscillation of the water in phase with the oscillation of the bottle? Can any of you answer?
Sorry, can you repeat the question, please?
So is the you showed that the periods are the same, but are the phases the same? Like when you have maximum angle, is the velocity maximum, zero?
Yes.
I mean,
well, of course, when the bottle is going on this way, then when the water is going to rise on the other side, then the velocity will be zero. And it will be maximum when the rise of the fluid will be at its maximum on the side where the bottle goes.
do you guys agree?
Yes.
Yes, it's in antiphase. So if you subtract the progressive velocity, it always looked as if the bottle was standing, and from the conservation of momentum, you can see that the direction of the velocity of the water is different than the direction of the velocity of the bottle.
Thank you very much to all of you. Ça va? You okay? So, juries, please put your marks. Are you ready? Okay. Jury, please show us your mark for the reporter team of ENS Lyon, France. We have 8, 9, 9, 9, 9, 8, 6, 5, and 7. Thank you. Jury, please show us your mark for the opponent team of Poland. We have 6, 5, 5, 4, 9, 7, 9, 9, and 7. Thank you. Jury, please show us your mark for the reviewer team of Russia. We have 6, 10, 8, 7, 6, 4, 9, 7, and 6. We will take the grades now. Just if you have some remarks.
Hello. I gave the lowest mark to the reporter, I think, that's because I should, and that's why I should start, I think, with commenting my marks. I think the reporter made a very nice presentation. It was really nice to see, and she has very good presentation skills. But I think the theory that was presented behind that, it was too simplistic, and the main and even worse was that the reporter didn't acknowledge this. She just said that I am not using the model solid sphere or solid semisphere, but she used it as I know, because if you know that the water surface is plane, that you use just this model. She said that she had some experiments on radius and on mass difference, but as we have seen, the theoretical results for the mass ratio were inconsistent, and the experiments were not presented. If you had made some more investigation, that you should clearly present it when you ask it about it, or you shouldn't say that you have made something about this. And that's why I have given you the mark of 5, because I think that the first one, the problem was not studied until the end, and the second one, that during the discussion I have seen some inconsistencies in your answers. As about the opponents, I think there will be many more comments. About the reviewer, I think you were a little bit aggressive, and that's why I have lessened your mark.
Sébastien?
Yes, I would like to react to the the theory is simple. You said it's simplistic or something. Well, it's great. Physics. This is exactly what physics does. Physics is reducing problems that look complex to the most important parameters and things to consider. And the fact that by identifying the right parameters and obtaining a theory which fits very well with the experiment is just wonderful. So you should not say that. I think it's unfair. As for aggressivity, this is very important. I gave a good mark to the reviewer, the Russian lady, because she managed in a difficult situation. You know, a scientific discussion should help progressing in the solution. It should be positive in the sense that we progress. The point is not to try to demonstrate that you are better than the other or whatever. You should never go into personal fights. You should have an obsession of finding the truth. And I found a lot of aggressivity from the opponent, and I appreciated very much the authority of the reviewer, who in this difficult situation, I repeat, found a way to moderate things and to progress and so on. That's why I gave a rather good mark to the reviewer. I was a bit critical on the attitude of the opponent, and I appreciated very, very much the reporter.
Micro.
Oh, first of all, I would like to commend the reporter. I was putting a relatively low mark, and I was trying to be consistent. I was selling Polish presentation previously. I have put 7. Now I think the Polish presentation was definitely better. So this was a very good presentation. Still, like compared to what was presented previously, it was not as good. It was not comprehensive by any means. So I think the science is about systematics. And in science, if you have some formula with parameters, you have to measure with every parameter and show that it systematically agrees. Unless it systematically agrees, it's not an agreement. If only one aspect is agreeing between theory and experiment, I wouldn't think that real scientists should be happy immediately. Yeah, you can shout, I'm happy, one thing is agreeing, but then you have to go for systematic and check everything. And that was not done. That's why the lower mark for the reporter. And then opponent and reviewer actually managed to make a nice discussion. I enjoyed the discussion, maybe the first time on this tournament. That's why I have put high marks, both to the opponent and to the reviewer. Thank you.
Thank you very much. So this was the last fight of the 8th International Physicists Tournament. Thank you again to all of our participants. There is a lot in the room also, so congratulations to all of you.